Vectors. A scalar has magnitude. It's just a real number. A vector, on the other hand, has both magnitude and direction. Some examples of scalar quantities are things like length, temperature, and speed. Some examples of vector quantities that you may have seen are things like velocity and force. Two vectors are said to be equal if they have both the same magnitude or length and the same direction. We will often represent vectors geometrically by drawing arrows. Here we see a picture of a vector v. Notice that we use a boldface letter for the name of the vector. Here we have a vector w. In this case, these two vectors are equal because they have the same length and they're pointing in the same direction. And it's worth mentioning that when you handwrite a vector, sometimes it's hard to distinguish between bold and normal typeface. So people will often use an italicized letter with a half arrow above it, as shown here. Some math books will even use this notation instead of the boldface. But when it's in print, I prefer to use the boldface for vectors. The sum of two vectors. Geometrically, we can add two vectors by placing the second vector's initial point at the terminal point of the first vector, as we've done here. Notice we have a vector v followed by a vector w. And we get the vector v plus w by starting at the initial point of v and ending at the terminal point of w. In this picture, notice in green, we started with the vector w and then attached the initial point of v to the terminal point of w. And when we draw the vector w plus v, we get the exact same vector as the vector v plus w. This shows us, geometrically at least, that v plus w is the same as w plus v. In other words, vector addition is commutative. The zero vector, written with a boldface 0, and of course, if you're handwriting it, you might write a 0 with a half arrow on top. This is the unique vector with length 0. Geometrically, we'll represent the zero vector with a point. The zero vector has the property that when you add 0 plus v or v plus 0, you just get the vector v. The technical term for this is that the zero vector is an additive identity for vector addition. Scalar multiplication. Okay, and what follows, the italicized k will be a scalar, meaning a real number. So k times the vector v is a vector that has length absolute value of k times the length of the vector v. If k is positive, then kv has the same direction as v. And if k is negative, kv has the opposite direction of v. And the vector kv will be 0 if either k is the real number 0 or v is the 0 vector. Here's a picture of a vector v. And notice that the vector 2v points in the same direction as the vector v, but has twice the length. The vector -1 times v has the same length as the vector v, but points in the opposite direction. We can also abbreviate the vector -1 times v simply as -v. And here's a picture of the vector -2v, which has twice the length of the original vector v, but points in the opposite direction because it's negative. Let's go over how to subtract vectors. Well, subtraction is just defined in terms of addition. V minus w means v plus the vector negative w. So if we draw the vectors v and w so that they both start at the same initial point, then the vector negative w we get by simply reversing the direction of the vector w. And now notice that this is set up perfectly to do an addition. When we add negative w and v, we get this red arrow here. And negative w plus v is the same vector as the vector v plus negative w, or v minus w, as we had previously shown. Now, starting with the original picture, we see that we can get the vector v minus w right away simply by going from the terminal point of w to the terminal point of v. Now, in practice, you may want to memorize this fact shown in the third triangle here, but you may forget which direction the vector goes. Does it go from w to v or v to w? So it's nice to remember this procedure. In particular, the intermediate step here where you actually reverse the direction of w and then perform an addition. That procedure is easy to remember long term, whereas just memorizing how the subtraction works using the third picture, you may forget in 6 months to a year from now. In this course, we're going to be focusing on vectors in 2 and 3 space. So here's a picture of a vector v in 2 space drawn in standard position. By standard position, I mean that its initial point is at the origin and its terminal point is at some point v1, v2. In this case, we can represent the vector in component form using angled brackets with v1 and v2 inside those brackets. Notice v1 and v2 in the component form of the vector are the same as the coordinates of the terminal point of the vector. You can only do this when the vector is drawn in standard position. v1 and v2 are called the components of the vector v. We could do something entirely similar in 3 space. Here we have a picture of a vector v whose terminal point is the point v1, v2, v3. And therefore, we can write the vector using angled brackets with components v1, v2, and v3, completely analogous to what we did in 2 space. Once again, remember, we can only write it this way when the vector is in standard position, meaning starting at the origin. If it's not starting at the origin, you will want to move it to the origin first, either geometrically or algebraically, so that you could see what the components are. 2 vectors are equal if and only if their corresponding components are equal. So here we have vectors v and w in 3 space. V and w are equal if and only if v1 equals w1, v2 equals w2, and v3 equals w3. Similarly, in 2 space, if we have these vectors v and w, then those 2 vectors are equal if and only if v1 equals w1 and v2 equals w2. We add 2 vectors in 3 space, component by component. So the first component of the sum is v1 plus w1. The second component is v2 plus w2. And the third component is v3 plus w3. And we do something completely analogous in 2 space as well, just 1 less component. Similarly, v minus w, we subtract component by component. And to do a scalar multiple of v, by the scalar k, we just multiply each component by k. Now's a great time to try an example. As always, you should pause the video first, try these examples yourself, and then resume the video to check your answers against mine. Okay, so here we have vectors v with components 2, -1, and 3, and w with components 3, 0, and 1. To get v plus w, we add component by component. 2 plus 3 is 5, -1 plus 0 is -1, and 3 plus 1 is 4. To get the vector negative v, we negate each component of v. So -2, the negative of -1 is +1, and -3. To get the vector 2v, we multiply each component of the vector v by 2. So we get 4, -2, 6. And to get the vector 2v minus w, we take the vector 2v, which we just found, and subtract the vector w by going component by component. 4 minus 3 is 1, -2 minus 0 is -2, 6 minus 1 is 5. Find the components of the vector from the point P1 with coordinates 2, 3 to the point P2 with coordinates -3, 4. The idea here is that to get this vector into standard position, we have to move the point P1 to the origin by subtracting 2 from the x coordinate and 3 from the y coordinate. Therefore, we should do the same thing to the point P2. So we get the vector P1, P2 in component form by taking -3 minus 2, 4 minus 3, and we get, well, -3 minus 2 is -5, and 4 minus 3 is 1. Okay, so here's a picture of what we just did. Notice that we have the given vector drawn in purple there, and we move it to standard position by moving the 2 to a 0 and the 3 to a 0. So we have to subtract 2 from -3 and 3 from 4 to find the terminal point of that red vector so that we get a vector with the same length and the same direction as the purple vector. So in practice, this just amounts to subtracting coordinate by coordinate, the terminal point minus the initial point, as we did here. Theorem. So we're going to list a bunch of properties about vector arithmetic. So first we have u plus v is equal to v plus u. In other words, vector addition is commutative. U plus v plus w is u plus v plus w. Vector addition is associative. U plus 0 equals 0 plus u equals u. 0 is an identity element for addition. And u plus -u equals -u plus u equals 0, saying that the negative of u is an inverse to u under addition. Okay? These properties together tell us that vector addition, together with the set of vectors in either 2 or 3 space, forms what's known as a commutative group or an abelian group. You don't have to know these terms for this course, but I just thought I'd introduce you to them in case you decide to go on to more advanced mathematics. Now, we also have some properties involving scalars. In particular, k times the vector lu is equal to the product of the scalars k times l times the vector u. Then we have two distributive properties. K times u plus v is k times u plus k times v. So a scalar distributes over the sum of two vectors. And we also have k plus l times u is ku plus lu. So two scalars distribute over a single vector. And finally, 1 times u is equal to the vector u. And now, anything that satisfies all of these properties has a special name. It's known as a vector space. For us, the only vector spaces we're going to be concerned with in this course are vectors in 2 space and vectors in 3 space, the ones that we already introduced. Okay, now, the proof of this theorem is pretty straightforward, a little tedious because there are 8 properties to prove. I'm just going to go through one in detail as an example. Let's prove the commutativity of addition, and we'll just do it in 2 space. The proof in 3 space is nearly identical. There's just an extra component. So starting with the vector u plus v, let's write that in component form as u1, u2 plus v1, v2. Now we use the definition of addition to get u1 plus v1, u2 plus v2. Now, inside those brackets, all those numbers, u1, v1, u2, and v2, are just real numbers. So we could use properties of real numbers. In particular, we could use the fact that addition of real numbers is commutative to rewrite u1 plus v1 as v1 plus u1, and u2 plus v2 as v2 plus u2. Then we could use the definition of addition once again to split this up as v1, v2 plus u1, u2, which is precisely v plus u. And we have successfully proved the commutativity of vector addition in 2 space. The norm, or length or magnitude of a vector, these 3 words all mean the same thing. Okay, in 2 space, the length or norm of the vector v is the square root of v1 squared plus v2 squared. And in 3 space, as you might have guessed, we get the square root of v1 squared plus v2 squared plus v3 squared. Here we have a picture of a vector v with component form v1, v2. Notice that if we have the vector in standard position, then starting from the origin, we move to the right v1 and up v2 to get to the point v1, v2. And the length of the vector v is the length of that hypotenuse of that right triangle formed. It's worth mentioning that some authors like to use double lines instead of single lines surrounding the vector v. The reason for this is to avoid confusion with the absolute value. Notice that I'm using the same symbol for the norm or length of a vector as you would have used for the absolute value in pre-calculus. There shouldn't be any confusion because you take the absolute value of a real number and you take the length of a vector. Also, if you think of a real number as a vector with a single component, then the length would be the square root of v1 squared, which is precisely the definition of the absolute value. So this definition actually generalizes the definition of absolute value to higher dimensions. Okay, that said, these are 2 different notations. They're both perfectly acceptable. I will be using the single lines throughout this course rather than the double lines. Okay, time to try another example. Go ahead and pause the video, try this example yourself, and then resume the video and check your answers with mine. Okay, so we have 2 vectors here, v and w. Let's compute the length of v. It's the square root of the square of -3 plus the square of 2, which is the square root of 9 plus 4, or the square root of 13. The length of w is the square root of 3 squared plus the square of -2 plus 6 squared. So 3 squared is 9, and then we get 4, and 6 squared is 36. Add those up, and we get 49, and the square root of 49 is 7. Now the length of 3v. Now we could compute 3v first by multiplying each component by 3, and then using the definition of the norm, or we could use this nice rule, this little theorem here, which says that the length of kv is equal to the absolute value of k times the length of v. Notice I called the first one an absolute value because it's a scalar inside, and the second one I called a norm or a length because it's a vector inside. So using this rule, we see that the length of 3v is the absolute value of 3 times the length of v. The absolute value of 3 is just 3, and the length of v we found previously to be the square root of 13. And we are done. Similarly, the length of -2w is the absolute value of -2 times the length of w, which is 2 times 7. Notice the absolute value of -2 is +2, right? Absolute values can never be negative. And 2 times 7, finally, is 14. So since we're using this rule, let's give a proof that it is actually true. I'll do it in 2 space. The argument is completely analogous in 3 space. So the length of KV, rewriting V in component form as V1, V2, and using the definition of scalar multiplication, we get the length of the vector KV1, KV2, which by definition of length is the square root of the square of KV1 plus the square of KV2. Okay, these are all real numbers now, so we could use rules for real numbers. In particular, we get k squared v1 squared plus k squared v2 squared under the square root. We could factor out the k squared and use the rule that a product under a square root is equal to the product of 2 square roots. The square root of k squared is, by definition, the absolute value of k. And to the right of that, we have the definition of the length of v, or the norm of v. A vector of length 1 is called a unit vector. There are 2 special unit vectors in 2 space. We name the vector 1, 0, I. Notice it's a bold-faced I because it's a vector. And similarly, the vector 0, 1, we give the name of j. Similarly, in 3 space, we have 3 special vectors, I, j, and k, for 1, 0, 0, 0, 1, 0, and 0, 0, 1. We can write a vector in 2 space in what I call ij form by splitting up the vector as follows. We could rewrite the vector v1, v2 as the sum v1, 0 plus 0, v2. If you don't see that right away going from left to right, do it from right to left. It's much easier. Just add those 2 vectors. V1 plus 0 is v1, 0 plus v2 is v2, and you should see right away that those 2 things are equal. Now, using the definition of scalar multiplication, we could rewrite v1, 0 as v1 times the vector 1, 0, and 0, v2 as v2 times the vector 0, 1. Now, 1, 0 is what we named I, and 0, 1 is what we named j. So we see that we can write the vector v1, v2 as the vector v1i plus v2j. So the form on the left is the component form, and I'll call the form on the right the ij form. Similarly, in 3 space, we could rewrite the vector v1, v2, v3 as v1i plus v2j plus v3k. So we have both the component form and the ijk form. Okay, and let me just point out once again that if we were handwriting I and j, we would probably do it with these little half arrows over the I and j, and similarly for I, j, and k. In these examples, I want you to write the vectors in ij or ijk form whenever possible. So go ahead and pause the video, try these examples yourself, and then resume the video to check your answers against mine. Okay, so the vector 3, 5 can be written as 3i plus 5j. The vector -3, 0, 2 can be written as -3i plus 2k. Now let's add these 2 vectors. So if we add the I components, 3 minus 5 is -2. For the j components, 2 minus -2 is 2 plus 2, which is 4. And for the k components, -1 minus 1 is -2. Okay, now the scalar multiplication, 3 times 2 is 6, and 3 times -5 is -15. Now for the last one, we have a length, or a norm. So we have the square root of 3 squared plus the square of -2 plus 1, which is the square root of 9 plus 4 plus 1, or root 14. Normalizing a vector. Given a non-zero vector v, the vector u defined by v over the length of v is a unit vector with the same direction as v. Okay, so sometimes we want to replace a vector by a vector in the same direction, but with a length of 1. That's called normalizing the vector. Let's just check that the vector u that we have defined this way actually has length 1. Well, the length of u is the length of v over length v, just a direct substitution there. Now, since length of v is a scalar, it's just a real number, we could write v over the length of v as 1 over length v times v. And using the rule we just used recently, we could write that as the absolute value of 1 over length v times length v. Now, the length of v is always a positive number because the vector we're given here is non-zero. So we could just remove the absolute values. And then we see that we get 1 when we multiply these two quantities together. Okay, try this example. Pause the video. Then resume the video and check your answer with mine. Okay, so find the unit vector that has the same direction as v equals 2i minus 2j plus k. We start by finding the length of the vector, 2 squared plus the square of negative 2 plus 1 squared. Take the square root. So we have 4 plus 4 plus 1 is 9, and the square root of 9 is 3. And we get our unit vector in the same direction by normalizing this vector, meaning we divide each component by the number 3 that we just found. So it's 2/3 I minus 2/3 j plus 1/3 k. Here we have a picture of a vector in standard position together with the angle theta that the vector makes with the positive x-axis. Okay, remember that the hypotenuse of this triangle formed here has length equal to the length of the vector v. From basic trigonometry, the legs have length v cosine theta and length v sine theta. For example, if you look at the adjacent side divided by the hypotenuse of the triangle, you get length v cosine theta over length v, which is equal to cosine theta, as it should be. Similarly, for the sine of theta. From this, we see that we can write a vector in 2 space as its length times cosine theta, comma, its length times sine theta, because those are the lengths of the sides of those two triangles there. Okay, in ij form, this is just length v cosine theta I plus length v sine theta j. For a unit vector, the lengths are going to be 1, so we just get cosine theta sine theta or cosine theta I plus sine theta j. Okay, let's try one more example. Go ahead and pause the video, try this example, and then resume it to check your answer with mine. Okay, so find the vector of length 2 that makes an angle of pi over 4 with the positive x-axis. So according to our formula here, we have v equals 2 cosine pi over 4, 2 sine pi over 4. Now the cosine of pi over 4 and sine of pi over 4 are both root 2 over 2. So this simplifies to the vector root 2, root 2.